Hi, and welcome to Module 5 of Lecture 7. In this module, we're going to discuss Bayes' rule. Now, in the previous module, we discussed combinatorics, combinations and permutations, and discussed how they were useful for calculating probabilities. Now, when they are useful for these things, they tend to be used less frequently than Bayes' rule, which is a bedrock of multiple types of quantitative analysis. Bayes' rule deals fundamentally with one thing, but a very important thing, which is to take a prior belief about some event's occurrence and transform it by incorporating new information you have about that event into a posterior belief about that event's occurrence. So again, you start with a prior belief, you incorporate data, and you create a posterior belief. In notation, you might start off with some belief about A, and that's going to end up going to some belief about A that's now conditional on some B, some new data, right? We're going from a unconditional probability, that is your prior belief about some event's occurrence, to a posterior probability, that is a conditional belief about some event's occurrence, conditional on the data, the information that you just obtained. This ends up being incredibly important in so many branches of analysis that it's worth its own module and probably more than that, because you use it a lot. The two major areas you see it are in statistics and game theory. In statistics, it forms the basis of what's known as Bayesian statistics. Now, we're going to discuss that a little bit more in the next couple of modules, not much more. This is not a class in statistics, it's a math course. But in order to give you a sense of why we're doing this, we'll talk a little bit about that. In Bayesian statistics, you start off with some prior distribution, and then you use data to form a posterior distribution. This comes from the exact same idea as Bayes' rule, which is why it's called Bayesian statistics. You're using information, data, to update prior beliefs. Game theory, it also is used in game theory when information is provided to you to update some prior beliefs about something or other into some posterior beliefs about something. A particularly common use of Bayesian, called Bayesian updating, Bayes' rule, in game theory occurs with games, the equilibrium concept known as the perfect Bayesian equilibrium, again with the Bayes. This equilibrium is most often seen in political science and what are known as signaling games. A signaling game is when you have two actors, or two or more actors, but the simplest one is with two actors. One actor is the signaler, the other is the receiver of the signal. The signaler has some private information about its type. So it might know that it's a mean or a nice player, or something like that. It knows what type it is. In common examples, you might see the signaler might know it's a hardline or a softline government, something like that. Or the signaler might know that it's an extremist or a moderate, or the signaler might know the state of the world, but might have incentive to lie about a different state of the world. All sorts of different possibilities. So it might be a good economy or a bad economy coming. The signaler has some private information about this. Now the problem is the signaler can't just tell the receiver this all the time, because the receiver knows that the signaler might have incentive to dissemble, to lie about the information, because the signaler might have different preferences than the receiver has. From the receiver, for instance, let's say the signaler is actually an extremist, but knows that the receiver wants a more moderate policy. The signaler might pretend that the state of the world is such that it demands an extreme policy, when actually the state of the world is such that a moderate policy would have been fine. The receiver knows that the signaler might be an extremist, or that the signaler has different preferences, and therefore can't trust the signaler's statement that the world is actually demanding extreme outcomes, and believes the signaler might be instead lying just to get the extreme outcomes that it wants. Right? There are many such examples of this kind of signaling game. And the way Bayes' rule comes into it is that in order to properly deal with such a game, the receiver must incorporate information gained by observing the signaling strategy of the signaler in order to form a new posterior belief about the type of the signaler. So the receiver starts off with some prior belief observes what the signaler does, what the signals sent are, and then updates the receiver's belief to take into account this new information. Bayes' rule, therefore, forms a prominent role in that as well. So Bayes' rule is very important. It's also sort of tricky from an empirical perspective. It turns out that a Bayes' rule is actually very counterintuitive in a lot of ways. Most people don't properly use Bayes' rule when they're updating information. It turns out we're pretty bad at that as human beings. And for instance, we're so bad that in medicine sometimes you often see doctors, well, on occasion you'll see doctors actually provide to you a list of odds, of updated odds of a particular illness that you might have based on the test results you've gotten, because individuals tend to freak out about, say, a positive test, even though because the actual underlying disease is very rare, even a single positive test doesn't necessarily yield a very high likelihood of you having the disease, given rates of false positives and false negatives. So Bayes' rule helps you actually use the information properly and not, say, overestimate the chance of something bad happening in that case. So that's Bayes' rule, and I hope that gives you a sense of why we're going to use it. Next thing we have to do is actually go into how it works. Before we do that, we're going to derive Bayes' rule. So let's start there. Okay. So Bayes' rule. It turns out we actually almost have derived Bayes' rule already. It's actually, even though the rule itself is reasonably long, well, it's not that long, the derivation of it is incredibly straightforward, and it comes from stuff we've done already. So, recall that the probability that A and B happen together is equal to the probability of A given B times the probability of B, which is also equal to the probability of B given A times the probability of A. Okay? Consider these last two statements, which are equal to each other. Make them equal, and then divide through by the probability of B. This is a very general form of Bayes' rule already. What it says is this: the probability of some event A conditional on observing some outcome B, some event B, is equal to the probability of B given A times the probability of A divided by the probability of B. So if, for instance, you had some prior beliefs about things, right? Probability of A might be your prior belief that A occurs, having not seen B already. This thing here, I'll make that in blue, this thing over here is the probability that B occurs conditional on A. Typically, that's some specific information that you gain in some interaction through some data. For instance, in game theory, that's usually dictated by the strategies that one player takes. So if you're the second player and A is a possible type of the first player, you have some prior belief, P of A, that the player is a certain type, is type A. Then they do something dependent on their type. You assign a probability that they do a particular action given a certain type. That's part of the equilibrium strategy. And we'll give an example of exactly that later in this module. Then you divide by probability of B, which is the unconditional probability that B happens, and B might happen when given A, it might happen given not A, or other things, right? And we'll get to that a little more. But the key notion is that you divide the probability that B happens given A by the probability that B happens for any reason at all. In that way, it's very similar to our notion of classical probability, where you divided the chance that A happens, the number of ways A could happen, by the number of ways anything could happen. Here we're taking the probability that B happens given A times the prior belief of A divided by the chance that B happens for any reason at all, not just if A happens. So it's a similar character. What this does is basically allow you to convert one conditional probability over here for another conditional probability over here, the one of interest. Here, this one over here, on the right in blue, this one is the probability that a type A person, for instance, might do action B. that's often given by an equilibrium notion. The one on the left in red here is the probability you want. It's the posterior probability that the person is type A given that you observed action B. And that's how you convert information from prior information over here into posterior information over here, posterior beliefs over here. And that's Bayes' rule. Now, I should say you don't often see Bayes' rule written in this form. The reason is the denominator is hard to deal with in this form. So instead, what you do typically is use an expansion of P of B, taking into account some mutually disjoint set, some mutually exclusive set of events. So let's assume we had some, let's go back. I'll write this over again here to keep it on the screen. We need some more room to do this though. Okay, that's B given A. Okay. Now often, let's say you have some mutually disjoint things A. Maybe A is just one of many things. So let's call this A sub J. It's one of many A's that are mutually exclusive. Right? But mutually exclusive means they're the chance that AJ and AK, where J is different from K, is 0, right? No two A's can happen at the same time. Sorry, intersection. They're A and the chance that that AJ and AK happen at the same time is 0. Sorry. Okay. Going back to this, if they're all mutually disjoint, you can expand PB into the sum over J of PB given AJ times PAJ. What you're basically saying is this. How can B happen? Well, given a set of mutually disjoint things, it could either have happened given A1 happened, or given A2 happened, or given A3 happened, and so on. Those are all these conditional probabilities. So the chance that B happens given A1 happened is the first one. The chance that B happened given A2 happened is the second one, and so on throughout the sum. So these are all the possible sums. So we have PBA1, PA1 plus PBA2, PA2 plus forever, right? Until you run out of things in your set of A's, A sub J's. So you take each one of these chances that B happens given A happens, and you weight it by the chance that that particular A happened, right? If PB given A3 is 1, because whenever A3 happens, B always happens, but A3 never happens, then B is not going to happen, right? So for instance, if you happen to have a situation in which that were 1, so maybe B is very likely to happen, except A3 never happened in the first place. That doesn't matter if B is guaranteed to happen after A3 happens, because A3 never happens. So you have to make sure to weight each one of these PB given A's by the chance that A actually happens. So that is expansion. How does it help us? We can put that in the bottom of Bayes' rule and replace this with this here and get a longer term in the bottom. And that's helpful because now we might know each individual PB given AJ, and we might know each prior probability of all the different AJs and can fill in the blanks that way instead of having to figure out some abstract chance that B happens no matter what's actually happening around B, right? And the top here, we have to know somehow the chance that PB happens, averaged over everything else. Here's the actual averaging happening down here, in which you actually can specify the chance that B happens given every single one of these A's. Now this too is not the most common way of seeing Bayes' rule. Typically we might consider only two actions that could happen, A and not A. This is often common in game theory in particular. In that case, we can simplify our sum over here and say that PB equals PB given A times PA plus PB given not A times P not A. because you have if A and not A, they form a collectively exhaustive, mutually exclusive set of elements, of events. And this allows you to form the most common way of writing Bayes' rule. So I'll write it one more time because it's just that important. And I switched to the normal way of writing Bayes' rule. I'm used to writing B given A. Not that it matters at all. They're just dummy letters. Just indexes. There you go. And this is what you see in the book first thing. And this is the most common way you probably have seen. You probably will see Bayes' rule when using it, when first using it. And this again allows you to switch from information, from knowledge about what type A would do, to adjusting your beliefs about the likelihood of observing a type A given what an unknown person did. Having now discussed what Bayes' rule is, derived it, and discussed why we care about it, let's do a brief example. Now in the book we have a couple of examples of a little more length. Here we'll do a different one that's a little shorter, just to give you a handle on sort of what it looks like. Okay, so again, let's write the last version of Bayes' rule one more time. So the goal, again, of Bayes' rule is to figure out what the probability of observing A is, or of observing A, the event A, given that you've observed B. Given that you know information about when B happens given A. Okay. So, here's again. Now, let's think of a story in which you have this particular setup. Say type A is a nice type, and say B happens to be cooperation. So a nice type will always cooperate just because it's just uniformly nice. So the probability of observing cooperation, B here, given the nice type A, is 1. On the other hand, let's say that a not nice type will cooperate half the time. So half the time a not nice type will cooperate, even though they're not nice. Let's cooperate anyway half the time. Now let's consider the prior beliefs about each type. Let's say you're a particularly cynical person and you believe people finding a nice type is unlikely. So the chance of observing a nice type is actually 1/5 in your estimation. And that means the chance of observing a not nice type, not A here, is 4/5. They have to add to 1. They're mutually exclusive and collectively exhaustive. So the sum of the probabilities must add to 1. Okay. Now, you observe B. Now, intuitively you might think, well, look, I know nice types always use B, and not nice types only use B half the time. So I observe B. So there should be a pretty good chance of nice type, right? Let's go to Bayes' rule. Bayes' rule says the chance of the type being nice, given having observed B, which is a thing a nice types always do, cooperate, is equal to P of B given A is 1 times the prior probability of A is 1/5 divided by that same 1 times 1/5 plus the probability of B given not A, which we said was 1/2, times the probability of not A, the prior probability of not A, which is 4/5. What's this? Well, it's 1/5 divided by 1/5 plus 2/5 equals 1/3. So even after observing B, a thing that nice types always do, right? Even after seeing cooperation, which nice types will always do, you still only think the chance that the type is nice is 1/3, much less than you might intuitively believe. Why is that here? Well, a couple reasons. One, you started off with a very low prior probability of believing they were nice. If your prior probability of believing they're nice were 1, for instance, then you'd have 1/1 plus 0, and you'd remain thinking they were nice, having observed them cooperate. So the higher the prior probability of that particular type is, of your believing that the type A is, the more the posterior probability will be, which kind of makes sense. This is incidentally why oftentimes people get unhappy about diseases, as you said before in this module. If you have that's said really poorly. What I mean was why a particular test might make people very worried about a particular illness, even if the illness is rare. If the illness is rare, the prior probability of observing the illness is very low. So even a positive test does not necessarily take your posterior probability up very high. Doesn't have to, at least. The other determining factor here is this 1/2. If it turned out that mean types, not nice types, never cooperated, then you would never see B played when you have not A. That 1/2 would be 0, and you'd have 1/5 over 1/5, which would be 1. In that case, the information B would be perfectly determinative. Having observed cooperation, you know it can't be a not nice type because not nice types never cooperate. Therefore, it must be a nice type. So because they never give the wrong signal effectively, in that case, you are never wrong. You learn everything by observing the particular signal. In game theory, this is referred to as a separating equilibrium, in which the different signals perfectly tell you what type you're playing with. So you're able to know exactly what type you're playing with. The different types separate. If you had a perfect test that was only ever positive when you had the disease, and you saw positive, then you would know you had the disease if you saw a positive test, because you could not have seen a positive otherwise. Those tests don't exist, by and large, so we generally don't have that ability to do that. But if that were true, if it were a perfect test, then you would see a 0 where the half is here. And again, you would have, even though you might have had an initially low prior probability of believing you had the disease, you would end up with a 1. You would know for certain you had the disease, having seen a positive test, if the test were perfect. And that's Bayes' rule. It helps us understand, you can see it helps us understand the chance that, it helps us understand what we should believe after observing information given our prior beliefs. It's sensitive both to the quality of the information you get and also to your prior beliefs about the events happening in the first place. Okay. So that's Bayes' rule. We have one more much briefer module at the end to go over a couple of minor points of probability before we move on to the next lecture's discussions of distributions. Thank you very much.